So, question 2. Well, let's calculate the range. Now the range is a word used for the horizontal displacement of the projectile, the maximum horizontal displacement just before it lands. So it's going to be this horizontal distance that the snowball travels through before it lands. So in our grid, to calculate the range, we need the horizontal displacement. Now we have 1, 2, 3, 4, 5 values here. We know u, v, a and t, and we've been asked to calculate the horizontal displacement, the range here. Now if we return back to our Suvat equations, what you'll see is, because the horizontal acceleration is 0, because there's no air resistance, this term is 0, so we get s equals ut. This is 0, this term, so we get v equals u. You can see that the horizontal velocity will remain the same. And basically the Suvat equations horizontally just boil down to, because this term is 0, become s equals ut. And this is a familiar form of equation, isn't it? It's displacement is initial horizontal velocity, which remains constant the whole time, times time. It's just basically distance travelled is speed times time. Now you can only use that equation if the speed is constant, which it is here. The initial horizontal speed will remain constant. So horizontally it just boils down to s equals u times t. So if we return to our question, calculate the range, it's fairly straightforward. Our initial horizontal velocity is 5 and that remains constant. We have our time of flight, 2.02 seconds. S equals u times t. So I'll just go back to work that through on a page, and if we just work it through below, S equals ut. Now again, if we just stress that this is applying to the horizontal, and this is really the only horizontal Suvat equation in projectile problems, because a equals 0. So we've got 5 meters per second times our time of flight, which was 2.02, and that becomes 10.1 meters. So if we return to our front sheet, plus 10.2 for our range, and if we just add a diagram here showing the approximate path of the projectile, we've now got the time of flight and we've got our horizontal range, 10.2 meters. Now we know when the projectile lands that horizontally its speed will still be plus 5 meters per second. But what about the final vertical velocity? So question 3, calculate the final, by final here we mean just before landing, calculate the final vertical velocity. And that's the only piece of information left in the grid, v, the final vertical velocity. Well, we have s, we have u, we have a, and we have t. We have 4 values in the grid. We only need 3 in order to work out v. So we've got our pick really of the Suvat equations. Let's imagine we didn't know t and we'd only been provided with s, u and a. And let's see which Suvat equation we'd need to use in order to calculate v. Well, it would be this one, v squared equals u squared plus 2as. No t in this equation here. So in order to answer question 3, to calculate the final vertical velocity, let's use the equation we've just mentioned there. So we've shown the working for question 1 earlier and question 2, and let's just show the working for question 3. V squared equals u squared plus 2as, and we're applying that vertically. Let's substitute in the values that we know. The initial vertical velocity is 0 plus 2 times the vertical acceleration is minus 9.81, and the final vertical displacement is minus 20. So that gives us v squared is, just calculate that there, 2 times minus 9.81 times minus 20, 392.4. So V will be the square root of 392.4, which is 19.8 meters per second. Now, you have to be careful here. With the square root, there are two possible solutions. If you the square root of 9 could be 3, or it could be minus 3, because 3 squared is 9, and minus 3 squared is also 9. So we've got to ask ourselves, when we square root, is this a plus or a minus velocity? Well, it's moving downwards, our snowball, and downwards is in negative direction, so our final vertical velocity will be minus 19.8 meters per second. And if we return back to our original grid, we can now add in minus 19.8 meters per second.